Alright, so in this lecture we are gonna be understanding the behavior of contrastive laws, which is explained in this paper in 2021. And this paper is really interesting it's a great theoretical paper for those people who are interested in a deeper understanding of contrastive laws and contrastive learning. Unsupervised contrastive learning has achieved outstanding success, while the mechanism of contrastive laws has been less studied. In this paper, they concentrate on the understanding of the behaviors of unsupervised contrastive laws. And they will show that the contrastive laws is a hardness-aware loss function, and temperature tau controls the strength of penalties on hard negative samples. The previous study has shown that uniformity is a key property of contrastive learning. We build relations between the uniformity and the temperature, and they will show that uniformity helps contrastive learning to learn separable features. However, excessive pursuit to uniformity makes the contrastive laws not tolerant to semantically similar samples, which may break the underlying semantic structure and be harmful to the formation of features useful for downstream tasks. This is caused by inherent defect of instance discrimination objective. So instance discriminative objective tries to push all different instances apart, ignoring the underlying relations between the samples. Pushing semantically consistent samples apart has no positive effect for acquiring a prior informative to general downstream task. A well-designed contrastive laws should have some extensive tolerance to the closeness of semantically similar samples. Therefore, we find that the contrastive laws meets a uniformity tolerance dilemma, and a good choice of temperature can compromise these two properties properly to both learn separable features and tolerant to semantically similar samples, improving the feature qualities and the downstream performances. Here we display two embedding distributions with 4 instances on hypersphere. And we observe that the exchanging xj and xk, as well as their corresponding augmentations, will not change the value of contrastive loss. However, the embedding distribution of A is much more useful for downstream tasks because it captures the semantical relations between instances. And for visualization, we always use TSNE algorithm and visualization of the embedding distribution for 2 different. You see that when the temperature is very small, you have a different distribution than when it is big. So small temperature tends to generate more uniform. This is more uniform distribution, and it is less tolerant to similar samples. So the contributions of this paper is that they analyze the behavior of contrastive laws and show that contrastive laws is a hardness-aware loss. They validate that the hardness-aware property is significant to the success of contrastive laws. With a gradient analysis, they show that the temperature is a key parameter to control the strength of penalties on hard negative samples. Quantitative and qualitative experiments are conducted to validate the perspective. And they show that there exists a uniformity tolerance dilemma in contrastive learning. A good choice of temperature can compromise the 2 properties. and improve the feature quality remarkably. So given an unlabeled training set X, the contrastive loss could be written like this, and this is the variable, this is the temperature that we are going to investigate and see if how it varies. For example, when temperature is too slow, you see that the gradient is too sharp. So the gradient ratio with respect to S is too sharp. And so S here is a feature extractor which maps the images from pixel space to hypersphere space. So for two images xi and xj, we can calculate this Sij for two images. But this is a contrastive loss for each of the images, and here the objective can be written like this, that you sum over all combination of I and j. When we fix I, then you go sum over all combination of I and j, and lambda again is a hyperparameter. So we define the probability of xi being recognized as xj. This is the probability of xi being recognized as xj. And then we analyze the gradients with respect to positive samples and different negative samples. We will show that the magnitude of the positive gradient is equal to the sum of negative gradients, and the temperature controls the distribution of negative gradients. So smaller temperature, when tau is small, smaller temperature tends to concentrate more on the nearest neighbors of the anchor points, which plays a role in controlling the hardness of air sensitivity. Specifically, the gradients with respect to positive similarity, Si and I, and a negative similarity, Si and J, are written here. And we are investigating the role of this temperature tau. So we consider two extreme cases when temperature is very, very small and very, very big. And here S max is the maximum of the negative similarities. And so when tau goes to 0, this case, the contrastive loss becomes a triplet loss with margin of 0, which only focuses on nearest negative sample. On the other extreme case, which is tau goes to infinity, this case, we approximate the contrastive learning like this, and you see that we use Taylor expansion of log 1 plus x and exponential of x, and omit the second or higher order infinitesimal term. And let's talk about explicit hard negative sampling. We study a more straightforward hard negative sampling, which truncates the gradients with respect to uninformative negative samples. Specifically, given an upper alpha quantile, we call it alpha quantile for the anchor sample, we define the informative interval and the uninformative interval. And then we force the gradient ratio which resides in the uninformative interval to 0. And the gradient ratio of x sub L residing in informative interval like this. And the above operation squeezes the negative gradients from the uninformative interval to the informative interval. So the hard contrastive loss is this. But this loss only penalizes the informative hard negative samples. The hard contrastive loss acts on hard negative samples in two ways. An explicit way that chooses the top k nearest negative samples, and an implicit way by the hardness of a property. So you see that how uniformity varies, trained with different temperatures. So when your temperature is too small, you have a very, very high uniformity. And by the way, this is minus loss. So the more the uniformity, the better it is. So that's why for smaller temperatures, we have very high uniformity. In fact, we have many models. When we want to see if it is good, we have alignment measure and uniformity measure. Some of your models may be here. Your paper may be here. Mine may be here. But the best one is here. We want alignment loss to be very, by the way, these are losses, uniformity losses. And we want the alignment to be as small as possible and uniformity to be as small as possible. These losses to be. But unless it is very supervised, no one has reached a very, very low alignment and very, very low uniformity. So still, this region is very unknown. We don't know how we should model the loss or what kind of architecture will derive us to this beautiful place. And so we have measurement of tolerance and models trained on C410, C4100, and other datasets. So this is the embedding uniformity. So we incorporate the uniformity metric that is proposed in this reference, which is based on a Gaussian potential kernel. So many people use these laws to check if their uniformity is good or not. So this is the uniformity of embedding distribution trained with hard contrastive laws. And measurement of tolerance and tolerance to potential positive samples. The objective of contrastive learning is to learn augmentation, alignment, and instance discriminative embeddings. The contrastive loss has no constraint to the distribution of the negative samples. However, with the help of heavy augmentation and a strong abstraction ability of deep convolutional neural networks, the negative distribution reflects some extent of semantics, which is illustrated. And however, from the above section, we have recognized that when the temperature is very small, the penalties to the nearest neighbors will be strengthened, which will push the semantically similar samples strongly to break the semantic structure of the embedding distribution. To explain the phenomenon in a quantitative manner, we measure the tolerance to the semantically consistent samples using the mean similarities of samples belong to the same class, which is formulated like this. So this L represents, this L here represents a supervised level of image. I is the indicator as usual. And we could see that the tolerance is positively related to the temperature tau. However, the tolerance cannot directly reflect the feature quality. For example, when all the samples reside in a single point of hypersphere, like if, then the tolerance is maximized, while the feature quality is bad. The tolerance reflects the local density of semantically related samples. An ideal model should be both locally clustered and globally uniform. The contrastive loss meets the uniformity tolerance dilemma. On the one hand, we hope to decrease the temperature to increase the uniformity of the embedding distribution. On the other hand, we hope to increase the temperature. Why? To make the embedding space tolerance to the similar samples. So for the ordinary contrastive loss, it is a compromise to choose the appropriate temperature to balance both the embedding uniformity and the tolerance to semantically similar samples. The dilemma is caused by the inherent defect of unsupervised contrastive laws that it pushes all different instances, ignoring their semantical relations. So you see the effect of this temperature, tau, and we here see that similarity distribution of positive samples and top T nearest negative samples. And here the performance comparisons of models trained with different temperatures. And after pre-training, we freeze all convolutional layers and add a linear layer.